ISBS committee, and especially Florent for inviting me to this young blood keynote. I won't be too long so that everyone can move to the tours. I know it's the most important things in the conferences, so just... What I will talk about today is how multi-level biomechanical modeling can help in both understanding sport movement and designing sport equipment. We didn't talk with Gerda before, but it is well known that human movement is multifactorial by essence, and a lot of disciplines can interact to produce a single performance. Obviously, there is also sport equipment that can affect this interaction and bring some different outputs of the performance. You just have to think about running a marathon with 2-kilogram shoes, and you'll see what the result is. There is also some other factors that can affect the performance, but I won't talk about them. I will mostly rely on the interaction in between the biomechanics and the sport gears. And I will try to focus on this interaction by looking at different aspects of the design of running shoes. Once again, we didn't talk with Gerda, but there is a cross-link in between the performance and the injury risks. So I will first focus on how the performance can be affected by sport gears. What do I mean by performance? I'm relying and I'm looking at the muscle-tendon complex and the interaction in between the muscle and the tendon while the movement is performed. And what we can expect for a better performance is a better functioning or better interaction in between the muscle and the tendon. However, classical motion capture as optoelectronic system or kinematics, force plates, EMG, accelerometers are not sufficient to get an insight, to get access to this level. And there is a strong need for musculoskeletal modeling to interpret and to analyze and to obtain the data at this level, so at the muscle tendon level. And usually, the musculoskeletal modeling that is used is based on hill-type muscle models. A hill-type muscle model is a 3-element model that includes, on one side, the muscle fibers. So it's a phenomenological model that is just aimed at representing the output and not the real physical interaction or the real physiological aspects of the contraction. This model takes into account the classical force length, so active and passive force length relationship at the muscle fiber level, as well as the force velocity relationships. And this fiber is coupled with a tendon in here, which also has some high linear properties or some high linear features. And combining these elements into a single model can give us insight into the inner functioning of the muscle. That is how the muscles are performing along the force length relationship or the force velocity, or how does the tendon store and release the mechanical energy during the movement. So we will use this model to answer this question. Do wearing shoes affect the muscle-tendon interaction or the mechanical functioning in between a muscle? 8 subjects ran at 3.3 meters per second under 3 different shot conditions. The first one is the barefoot shot condition, so no shoe. The second one is a 0 millimeter midsole thickness, which is close to a minimalist shoe. And the last one is a 16 millimeters height of the midsole, which is close to a classical running shoe. Complete motion analysis were performed on the subject, that is measuring joint kinematics, ground reaction forces, as well as EMG data of the whole lower limb. Once we got all the data, we use them as input to a musculoskeletal model to estimate both muscle forces as well as fiber behavior. Just to give you a quick overview of how the model works, we use the kinematics data in order to drive a geometrical model of the lower limb that gave us the muscle tendon length and the muscle tendon momentums through the whole movement. We also use EMG data to get the muscle activations. These activations were used as input to the heel-type muscle model I was talking about earlier. After several steps of calibration and optimization, we are able to estimate what's really the key of the movement, basically, the muscle forces, because everything starts from the muscle. So we run all the subject and all the data to this model in order to estimate the muscle tendon forces, and we compare for the influence of the three different shoot conditions. Disappointingly, no real visible influence of the shock condition was seen on the ground reaction forces, the joint kinematics, except at the ankle joint level, and I will go back to it further on, the EMG activations, as well as the muscle forces. In here, I just plotted the amount of forces within the triceps surae that is done by each muscle, so the lateral gastrocnemius, the medial gastrocnemius, as well as the soleus muscle, depending on the shot conditions. And what you can see is that there is a slight decrease, but it's not significant. So the amount of force that is produced by each muscle within the triceps surae muscle group is kept constant, whatever the shot condition. Interestingly, some other results were significantly different. The first one is the range of motion at the ankle joint. So it's a known result that when you are running barefoot, the range of motion at the ankle joint increases. And in our data, it increases almost of 10 degrees with respect to the shot conditions. So we have a higher ankle joint range of motion with when running barefoot. But this increased range of motion at the ankle joint is also interlinked with a decreased fascicle excursion, meaning that the change in fiber length when running barefoot is less important than when running with a shoe. So it's statistically significant for the gastrocnemius medialis and the lateral gastrocnemius, so two biarticular muscles, and not significant for the soleus muscles. So going back to our question, how do running shoes influence muscle tendon mechanics, or the interaction in between the muscle and the tendons? From our results, wearing shoes can affect the muscle tendon interaction. And this influence can potentially have an effect on muscle fatigue, as well as the feeling of comfort during the running. Why do I say that? Basically, when you are relying on the muscle to produce a movement, it's energetically inefficient. Basically, you have to activate your muscle. It takes energy to contract and to produce a force. So it's not really good to rely on this part to get the movement done. Oppositely, if you are relying more on the tendon, that is, you are less using the muscle fiber and the excursion of the fascicle is lower, while the increase in tendon length is higher, you are storing free energy, mechanically free energy, to do your movement. And so it's potentially better for the muscle fatigue as well as for the feeling of comfort. So that's one part, that's the performance. What about the injuries? From now on, I will focus on the foot. It's well known that the foot is a key structure in locomotion. But, as you might know, it's also a really complex one with lots of bones, joints, ligaments, joints. And this complex structure makes it really prone to injuries, but also hard to analyze, treat, and repair. If we want to do all of that, analyze, treat, and repair, we should be able to estimate the stress and strain over the anatomical structures within the foot. And doing that is highly challenging. And there is a need for multi-level or multi-scale biomechanical model to answer this question. In order to estimate the stress and the strain over the elements, you have to take into account the muscle forces that can change the loads on the bones, for example, or on the ligaments, but also all the bone, tendon, ligaments, all the geometries of these different structures, as well as their material properties. What we did was to build an EMG-driven 3D finite element models of the foot. How did we do that? We used the muscle modeling part I just presented in order to get the muscle forces during the motion. And we also use a bunch of acquisition in order to build a finite element model of the foot and to be able to drive it using the EMG data. The finite element model building is a classical one. So we use geometrical acquisition using medical imaging data. We also used material properties taken from the literature or direct experiment, as for the heel pad, for example, using CT scans, MRI, X-rays, in order to be able to obtain a geometrical structure of the foot. Once meshed, this structure looks like that. So it's a foot that includes all the anatomical elements, plus the tendons. And we have included 9 tendons in this finite element foot models. And the tendons are basically stimulated, or we pull on the tendons using the previous forces that I just presented earlier. And this finite element model is dynamically driven in order to get the simulation point. So once again, the movement is a consequence of forces applied on the tendon. And here is one of the results for a working cycle. So you can see the movement. And something that is really interesting when you are looking at injuries, or when you are willing to get to the stress and strain over the elements, and something that you cannot do with real subjects, we remove the skin. We remove the skin, and we get access directly to the local tissue loadings that are available at each time step and for each structure of the foot. And you can see during the video here how for example, the loads on the Achilles tendon or on the ligaments on the front part of the foot are affected during the motion. Obviously, with all the models, you have to go through a validating step. I'm only presenting one curve that represents the ground reaction forces, so the vertical in black and the horizontal in red part of the vertical ground reaction forces, both measured by the force plate in solid line and estimated through the finite element model using the dashed line. So we have quite good agreement in between the curves, and that's the same thing for the kinematics and all the other aspects that we use as a validation. So we have a 3D finite element model of the foot. How can we use it to design new shoes? We just put a finite element model of a running shoes around the foot. And I'm only presenting here the midsole behavior. And so you can see that the midsole follows the foot, obviously. And what's interesting is that now we can have access to the internal stresses, the internal loads, while the motion is performed. And focusing on these loads, new running shoes can be designed, for example, to minimize internal stress in order to avoid stress fracture or other injuries that can occur while running. So to sum up a little bit everything, First, musculoskeletal modeling has shown that sport gears could definitely affect the biomechanical functioning of the muscle-tendon complex. And there is possible implication for feeling of comfort as well as muscle fatigue or muscle damage, at least during running, and that's something that we are currently investigating. And the last part is that multi-level biomechanical models can help in designing new types of sport products that will aim at minimizing injuries, at least the one relying on stress factors. But there is also, obviously, long-term studies that are needed to validate the future design of the muscle, of the products, sorry. And to do that, there is only one way to find out. It's to go out for a run, collect data, and see what's going on. So I would like to thank, once again, the ISBS organizing committee and Florent for the invitation, everyone that participated in the work in Marseille, and also the funding agencies that were of great help for this work. Thanks a lot.
Richard Smith, University of Sydney, Australia. Thanks very much for your very interesting talk on an area that's close to my heart and mine. I was wondering what sort of model for the foot you were using in those initial studies where you got large range of motion at the ankle joint.
It's single segment foot model that is classically used in motion capture data, but it's also seen when you are looking at more specific multi-segment foot model, when you are specifically looking at the rear foot versus the tibia movement, and that's the same results that are coming out. So you have an increased range of motion in between the rear foot and the tibia while running barefoot.
Thank you.
Any other questions?
Bruce Elliott, the University of West Australia. A lovely presentation. I have a question as an extension of the ankle. You may design a shoe that reduces loading for specific parts of the foot and the ankle. How can you be sure that that's not influencing the loading that occurs, let's say, at the knee? And has anyone ever thought of doing a model that actually links the ankle and the knee together as a pair?
Yeah, it's kind of something we are working on. So trying to gather all the joints. The actual problem is that it's for running the simulations I just show you. It's a day long. So increasing the number of elements, increasing the muscle forces and the contacts and the interface and everything, it basically adds up exponentially the computational time. So it's not that easy, but it's something we are working on. And we also know that from inverse dynamics and biomechanical analysis of running, there is a shift of the load from the ankle, from the knee to the ankle when running barefoot. So that's why we are also focused on the foot. But it's a really interesting question, and that can basically also drive to different shoes that can affect the direction differently. I mostly presented sagittal plane kinematics and ground direction forces, but it's a 3D model, so we can also have the mediolateral effects of the shoes, and that's something that's really interesting. Slight problem of overlay, but if we look specifically at the ankle joint, we can think of shoes that will affect differently the medial and lateral part of the ankle joint.
I'm Benedict van Ansen from KU Leuven. I have a question a little bit similar to what Richard was saying. So, as an input for your finite element model, you take kinematics. And I was just wondering, are you taking then the kinematics of a one-segment foot model? Is that accurate enough to actually model then the movements of the bones? Because you go in really detail and you actually have an input of one segment.
So we are not relying on the kinematics to drive the foot. That's the basics. We are relying, as in real life, on muscle forces. The only kinematics input that we used are the initial foot velocity and the foot ground angle just before the impact. So it's not a kinematics-driven simulation, it's a force-driven simulation. So we just use the muscle forces through the whole gait cycle or running cycle, but we didn't constrain for the kinematics. So that's the interest.
Use this opportunity to go a little bit further. What kind of contact model do you use? Because if you rely on the types of variables that you mentioned, then the contact, foot-ground contact or foot-sole-ground contact will be crucial.
So it's not an a priori contact model, it's just a penalty contact model where we don't allow the different elements to penetrate each other. But as we have all the mechanical properties of the structures, as the heel pad, basically the muscles, the sole, and the ground, there is no need for a precise contact model. It's only a penalty one where we are not allowing basically the elements to go from, for example, the foot to the ground.
So you don't contact the impact itself.
No, and that's the beauty of the model is that while not using a contact model, a specific contact model, we are able to get some force data, some ground reaction force data that really matches with the experimental ones.
I think this summarizes a very good talk. I think Guillaume deserves a round of applause for sure.